Dear esteemed colleagues, this is Mohammed Khenfouch. I wish you and all your loved ones are doing well in this difficult time, hoping to come back to our normal lifestyle soon. I would really like to thank the organizing committee of ISyDMA’5 for their invitation and the huge efforts they put to organize this event virtually. My talk will be about advanced 2D materials and their applications. This will start with an introduction about 2D materials, then some of the synthesis and characterization techniques and applications, and later some of the conducted projects. About UNISA, the University of South Africa, it is viewed as a leading distance learning higher education institute, known as one of the biggest universities in the world with nearly 500,000 registered students, and campuses in many countries and examination centers everywhere in the world. And its electronic library is regarded as one of the richest libraries. Recently, the university established its campus of science, engineering and technology, and with advanced laboratories equipped by state-of-the-art systems and techniques, making from them one of the best in the World South, and open for collaborations, especially for African fellows. Advanced materials were used for many centuries, and here I'm showing the known Leucogus gap, which is showing different colors at different lights. While it is a reflected light, the cap is green, and for the transmitted light, it is red. On the right side, a Maya figure in which they used a blue paint. It was found that this paint is very resistive and the color is slightly shiny. And the recent studies showed that this paint is actually a mixture of an indigo and polygoscite. And for the Madagascar seal sword, it was found that it is one of the very light and very strong and very sharp sword, and the recent analysis showed that these swords are containing carbon nanotubes. The tree of low-dimensional materials is growing, and each day we are discovering new materials, or we are making new materials from 0, 1D, 2D to 3D with different structures, alloys and materials. This is also the case of 2D materials. While till few years we were talking only about very few cases like graphene, clay and others, now we are talking about families of 2D materials, from MXenes to xenes to transition metal decalinogides, nitrates and organic materials. These materials are known by their unique properties, as everything is happening in the surface. About the synthesis techniques, there are some which are chemical and others which are physical. For the physical ones, most of them are using the principle of evaporating atoms, then collecting them on top of a substrate, like the case of PLD, for example. While for the molecular beam epitaxy, there are sources of atoms which are depositing these atoms on top of a substrate. For the chemical methods, basically we are starting with precursors that we are mixing to have sort of chemical reactions, which we are boosting by adding some catalyst elements. So basically these precursors will interact, and then the growth, nucleation of the particles will start, then the growth will start after that. Of course, here we have to take care about the pH level, the temperature, the pressure and so many other elements. The CVD, which is the chemical vapor deposition, which is a technique between the two, where we are using a gas. It can be a methane or any other source. It depends on the material that we are planning to grow. This gas will be heated and then we will see the atoms starting to be deposited on top of substrate to grow our material. And this is one of the methods that are commonly used to grow graphene layers. About characterization techniques, it depends on the properties that we are looking to study. For example, here for the XRD, so it is mainly used to study the structure of the material. And the XRD also can furnish different information. This includes the phases which are in our materials. The XRR is giving us an idea about the thickness of the materials, while SAX mode can give us an idea about the size of our materials. For the optical properties, many are starting by the UV spectroscopy, which is basically a technique allowing the study of interactions between light and matter. So the material will absorb the light and part of it will be used, then the other will be transmitted. So the difference between these lights can give us an idea about, for example, the gap of material. And if we do have different compounds, this will allow us to see how these elements are interacting between each other. And this is very important, especially for applications like in solar cells and others. To see how these particles or layers are looking like, we are using the electron microscopes. And here we do have two types, the TEM and SEM, with different resolutions. Physical phenomena are happening, so while irradiating the surface of the material with an electron beam, so OJ electrons, X-rays, photons are generated, and we can use each of us to study something in our material. So like for example, we can, of course, in addition to the images, we can have an idea about the crystallinity of our materials, and also we can use these techniques to have the distribution of our elements in the material and the composition of the atomic composition of our material. And in addition to this, we can also study the electroluminescence of materials using these techniques. For the vibrational properties, we are using a Raman spectroscope. Basically, while our material is excited by a laser, these molecules inside the materials are vibrating. This depends on the energy they received and also on the way these elements are vibrating. So for each mode of vibration, as listed here, like symmetric stretching, asymmetric stretching, wedging, the rocking, the scissoring, and twisting. So each mode is having its own fingerprint, its own peak in Raman spectroscopy. These techniques can help us to study, for example, the interactions between different compounds, to follow the growth of materials, and also to determine the impurities in our samples. The FJR spectroscopy is having similar principle as the Raman, with a simple difference between the two is that the Raman is active for a special range, optical range, while the FJR is active for a different range. So here we have to know that each of these two techniques are completing each other. So some of the vibrational modes are appearing in Raman, but they can't appear in FJR, and vice versa. These materials are touching everything in our lives. They are used in energy, in sensing, in cleaning water and air, and also for health-related applications. So for the energy sector, we are talking about the energy storage, conversion, and production. For sensing, we are talking about gas sensors, for example, and bioimaging. And for health, we are talking about toxicity and drug delivery. And for the environment, we are talking about cleaning the air and purifying water and so many other applications. In our group, we are developing materials for different applications. This includes solar cells, light-emitting diodes, electrodes for energy storage devices, applications for fluid quenching. We are developing polymer nanocomposites, and we are developing composites for water cleaning applications. And also we are using the green chemistry to produce a big range of materials. Graphene is our main material. It is considered as the mother of all allotropic carbon-based nanomaterials. This includes diamond, graphite, carbon nanotubes, and others. Due to its promising properties, it attracts the interest of many researchers and engineers. And there were too many organizations which were born based on the services and activities related to this material. To produce graphene, two main techniques were adopted. The first one is the known modified Hammers method, which is consisting of the exfoliation and oxidization of graphite particles to isolate graphene layers. This needs strong oxidants, of course, to separate the elements, and also there is a process of reducing the functional oxygen groups from the surface of graphene. The second one is simply the CVD, which is consisting of using a gas of, for example, an alcohol or any source of carbon to produce carbon atoms which are going to be deposited on top of a substrate. And here I'm showing some of the samples that we produced. This includes solutions and powders. So we did analysis to confirm the production of few layered graphene sheets. So this includes XRD and Raman, which is regarded as the most useful techniques to study graphene related materials, in addition to XPS and many others. So as the results shown, so there is a wide broad peak of XRD around 26, and there are the so-called 2D peaks which are confirming the production of few layered graphene. The same images are showing semi-transparent graphene layers, so which means that the product is formed of few layered graphene sheets. In this project, what we did simply is to use a plant which is well known in Morocco and in North Africa, which is Artemisia alba, Sheikh in Arabic, to remove the additional functional groups after the process of exfoliation and oxidization of the graphene layers. So the XPS results are confirming the removal of many functional groups, and this was also confirmed by photoluminescence. As you can see, for the case of few layered graphene oxide, there is an intense emission band which started to disappear after the reduction of functional groups from the surface of graphene using the plant extract. Nanofibers and electrosponges are known by their applications in too many sectors. This includes membranes and textile. So in this project, we synthesized nanofibers which are containing graphene layers with different concentrations and different sizes. And the main idea of this project was the isolation of one fiber, believing that such operation will be very important, especially for electronics. For water-related applications, we used several materials, and titanium dioxide was one of them. So the idea was to remove contaminants from water, especially the contaminants produced by textile industry. So the results were really interesting, as shown, which confirmed the removal or the degradation of such contaminants using different concentrations of these nanoparticles. In this slide, I'm showing a project that we conducted in collaboration with the University of Linköping in Sweden, where we fabricated a LED based on graphene and zinc oxide. The challenge was to produce a clear white light from one chip, and as shown, the light that was emitted by the LED was from 400 to 800 nanometers covering the whole visible range, and the curve that we obtained is showing a normal behavior of a light emitting diode or a diode. And as shown by the same image, this chip was based on Z nanorods and graphene layers. In the frame of bilateral collaboration between UNISA and the University of Limoges in France, we conducted a project in solar cells where we fabricated two different types of devices, an organic solar cell and a perovskite solar cell. It is known that graphene sheets can be used as transparent conductive layers, but if modified can also be used as whole transport layer, and also can be used as electron transport layer, and this was the case as we combined them with titanium dioxide to enhance the efficiency of the perovskite solar cell. In this project, we were able to see how graphene oxide layers can affect the morphology of a polymer. And also we studied the different interactions between the two elements which can affect the efficiency of the solar cell. And here we detected a charge transfer as well as energy transfer between the two systems. In another project related to solar cells, we studied the interactions between porphyrins, which are known as light harvesting materials, and graphene-based materials. So these interactions affected the optical properties of the whole system, where we identified charge transfer between the two systems, leading to an increase in the exciton lifetime, which is very important for solar cells. And with this I will conclude my talk, and I would really like to thank all the collaborators and sponsors of this project. And many thanks to the organizers and participants, and please feel free to contact me by email. Thank you.